So we still got a couple minutes. I know one time we were here early and someone requested to see Naruto, and it was down. But since then, at least like Mobile Legends has been reinstated. It's in the Apple Store, so I haven't checked the Naruto. So let me see if that's back. Let me see if that's there. If I get that same error I got before. Join. I don't know. It's not really doing it. Oh, it says loading, so we got like about a minute, a little over a minute. Might have to check it later. 1 minute, 10 seconds. Yep. Uh-oh.
ナルトクロスボルト忍者ボルテージ
The game is decent. Well, at least my main game is back up. I don't know. I've seen like gameplay where, you know, they've done like a cross between like Naruto, I think maybe some Dragon Ball Z and Mobile Legends, but I don't know how to get access to it. It does look like fun. Like they had Naruto as Lucas. I know y'all probably don't know these characters, but because he transforms into like the nine-tailed fox. I think I prefer Naruto as Sun with the shadow clone. So. All right, so we got about 10 seconds and we'll get the party started. And like I don't know if any of you all play Mobile Legends or not, but they recently did an update with like Hanzo. I had to adjust my build for him. I had to make him do more like burst damage. Assassin. But anyway, okay. All right. So I have that it's that time. Welcome back, gentlemen. I hope everyone had a great weekend. You know, either it was rejuvenating or productive, or you know, you did either what you wanted to do or what you needed to do. Just hopefully you're able to position yourself, you know, to advance yourself in your journey. Oh, so my body is definitely like responding to the weather. It was cold. I've been having aches and pains. I can't move. Like, what's going on? But I've noticed that as it's warming up, those pains are subsiding. I was like, that's a real thing. So, anyway, let me see. So, I think that exam one was due about a minute ago, right? Pretty much right now. So I'll do my best to try to update grades. Siri, turn the heater off. I'll do my best to try to update grades. You know, I guess within a week or so. It should be updating automatically. So you know, I would check your grade in Blackboard, and you know, if anything looks out of order, like if you know you submitted something and it's not showing up, you know, just check that. With attendance doesn't affect your grade. The only way it affects your grade if you get like 4 or more unexcused absences, then what could happen is you potentially be dropped from the course, and you may or may not be able to get back in. Right. So two main things that I'm looking for from you all: basically get your daily attendance by showing up to the Zoom and just zen out. You know, I don't harass you. Just as long as you show up and zen out, that's I feel like that's not asking for too much. So get your daily attendance and then just submit your assignments promptly with satisfactory scores. You get a lot of leeway there as well. Limited attempts. Essentially, it's not proctored. So, you know, again, on my end, I really just want to expose you guys to these concepts and encourage you to learn as much as you can, right? That's really the structure here. We're not like in a traditional classroom setting, you know, proctored exams, paper and pencil. Just tune in, ask questions, try, and it's okay to collaborate. Like it'll be okay. If you have questions, feel free to unmute yourself or type in the chat or the Q&A. We'll make sure to get those inquiries addressed. And I can't think of anything else. So So again, we just completed exam one. Again, your grades should update automatically. My intent originally was to design it so that the grades update automatically. So just check Blackboard for accuracy. And we're going to go ahead and move into chapter 3, right? So the bulk of this course is kind of like focused on derivatives. Like, if you don't learn anything else, at least on some level, you'll be somewhat of a master of the derivative, right? Again, the derivative is the slope of for our context, for the most part, derivative is the slope of the tangent line at a point, essentially. And we're going to kind of continue with like exploring some concepts there. So this week will be the last week that we do like 4 sections in a week. So I think our goal for today is to do 2, let me see, 37, 37, 6:37. Hey, Google, set an alarm for 6:37 p.m.
Done. Your alarm set for 6:37 p.m.
So yeah, we'll try to shift into the second half around that time. Okay, I can't think of anything else. So let's see. That looks good. All right. So we're going to move into chapter 3. Chapter 3 are applications of the derivative, right? Applications of differentiation, okay? And so section 3.1 is going to be using the first derivatives to find max and min values and sketch graphs. Okay, this is fun. I enjoy this. Like, I don't know why I enjoy it, but I just do. It makes sense to me. It's very visual, and so we're going to see how the derivatives, how these like show up and like in what context, aside from the slope of the tangent line, there's other information that it gives us about these functions, right? So that's what we're going to be looking at. Using the first derivatives to find max and min values of the original function. Let's take a look at it. A few objectives here. 1, find relative extrema of a continuous function using the first derivative test, and then 2, sketch graphs of continuous functions. Yeah, that gets fun, right? So a few definitions. A function f is increasing over interval I if every a and b in the interval I, for every a and b in the interval I, whenever a is strictly less than b, then f of a is strictly less than f of b. So for an increasing function in a graphical sense, as we trace it from the left to right, so whenever our a is strictly less than b, the corresponding f of a is strictly less than f of b. So in other words, as we trace the image from the left to right, the graph is going to be going up, right? So that's what we mean by an increase.
That should be blowing me.
That's what we mean by an increasing function. Give me just a moment. So let me see. I think we're good. But let me just have this ready to go. Come on. Where is it? Okay. Nope. This one. All right, cool. All right, we're going to let that jump. Okay, yeah. So an increasing function, again, in the pictorial sense, as we trace it from the left to the right, the graph goes up. If the input A is less than the input B, then the output for A is less than the output for B, right? So that's what we mean by increasing. We say a function is decreasing over interval I if for every A and B on the interval, whenever A is strictly less than B, then f of A is strictly greater than f of B, right? So increasing and decreasing in the technical sense, the definitions are the same. It's just that, for decreasing, the f of A is strictly greater than f of B. So in other words, if the input A is less than the input B, then the output for A is greater than the output for B. So in a pictorial sense, whenever we trace the image from the left to the right, the graph falls. It falls as we trace it from the left to the right, okay? So don't read, the technical stuff is just there. The main takeaway is you can understand the pictorial representation. Increasing mean as we trace it left to right, the graph is always going up. Decreasing as we trace it from the left to the right, the graph is going down. Okay, so then we have this theorem. So let f be differentiable over an interval I if f prime is strictly greater than 0 for all x in the interval I, then f is increasing over that interval, right? So the first derivative, right? So if the first derivative is positive, then all x in the interval are going to be increasing, right? So remember we said that the derivative is the slope of the tangent line at a point, right? So then if our first derivative is positive over an integer, that means all our slopes are positive. That means that over the interval, the graph is increasing, right? So whenever we have the first derivative is positive over an interval, as we trace the graph from the left to right, that means the original graph is increasing. Positive first derivative means the graph is increasing. So, it stands to reason that a negative first derivative over an interval means the graph is decreasing, right? So if you think about the slope of the tangent line, that kind of backs up that notion of increasing versus decreasing, right? So you can kind of flow between whichever one makes more sense. But for this context for today, the takeaway is a positive first derivative, the original graph is increasing over that interval. For a negative first derivative, the original graph is decreasing over that interval. Okay, hopefully that makes sense. So then the next idea or definition that we need to introduce is what's called a critical value, right? So we've been exploring as graphs increase from left to right, as graphs decrease from left to right. So then what do we mean by a critical value? Well, a critical value of a function f is any number c in the domain of f for which a tangent line at that point is horizontal or where the derivative does not exist. So in other words, the critical values are going to occur when our original graph is either at like the peak of a mountain or the bottom of a valley. And there's like kind of like one other, let me think. Yeah, or things we also consider critical values where the first derivative does not exist, right? Yeah. So we'll see how to find these candidates for the critical value, right? So what we're doing, if we're considering our original graph, we're breaking down, okay, how to tell where the graph is rising, how to tell where the graph is falling, how to tell where we have the top of the peak of a mountain, how to tell where we have the bottom of a valley, these kind of things. This is what the first derivative test is going to be revealing to us, right? So that is, C is a critical value if f of c exists and f prime of c is either 0 or if f prime of c does not exist, okay? So our critical values are going to occur when the first derivative is either 0 or where the first derivative does not exist, okay? So we'll get a function, we'll go ahead and calculate the first derivative. If we want to find our critical values, we're going to find those values of c where the derivative is either 0 or where it does not exist. Those are going to be our candidates for our critical values. And there's a little bit more to the test to see what's going on either side of those critical values to confirm that they are, but this is the structure of the setup. Hopefully this is okay. This isn't like information overload. Hopefully the image is coming together. And we're going to see this in practice momentarily. So if c is a critical value of a function f, then the order pair c comma f of c is going to be a critical point. So critical values like the x coordinate, the critical point is the x with the y. Okay. More definitions. Okay, so hopefully we're all aboard. Hopefully this makes sense. Again, the main takeaway, the main concept for today that we're exploring, how to identify where a function is, the original function is increasing, how to identify where the original function is decreasing, how to identify the maximum value, like basically the peak of the mountain, how to identify the bottom of the valley. Is there a question? Going once, going twice, mute. Okay, did it work? Yeah, okay, I think we're okay. Right, so increasing, decreasing, peak of mountain, bottom of valley, that's essentially what we're exploring here. Okay, so let I be in the domain of f. Then we say that f of c is a relative minimum value, again, that bottom of the valley, if there exists within I, thank you, there exists within the interval, an open interval I, containing c such that f of c is less than all nearby y values for all x in interval I1, okay? So again, relative minimum, we say that whenever we have some y value that's less than all nearby y values, in other words, the bottom of a valley, right? We're going to pretty much be working with these pictorially, and we're going to be backing up these notions by exploring use of the first derivative. And then we say that f of c is a relative max if there exists a interval I, an open interval I, within I, an open interval I2 containing c such that f of c is larger than all nearby y values, right? So we say it's a max if we have some y value that's higher than all the nearby y values, right? And again, using the first derivative test, it's fairly simple, I mean, for the most part. So then theorem 2, if a function f has a relative extreme of value f of c in an open interval, then we say that c is a critical value and that f prime of c is either 0 or it does not exist, okay? I really just want to get into an example. Let me see, there's another theorem. So the first derivative test for relative extremes. So I think I've mentioned it, so let's formally go through it. So for any continuous function f that has exactly one critical value c in an open interval, F1, F has a relative min at C if F prime of X is strictly less than 0 on the open interval from A to C, and F prime is positive on the open interval from C to B. That is, F is decreasing on the left of C and increasing on the right of C, okay? So this first property of the first derivative test, let me see. So say we've identified our critical value. Again, the critical values occur when the first derivative is either 0 or it does not exist. And then, so we have this X value for a critical value, and then it breaks the number line up into different sections. So then we're going to choose some values on the left of that critical value, take the first derivative. If we get a positive result, that means the original function is increasing. Then we're going to choose a value on the right side. We're going to choose a value on the right side of that critical value if the original function is decreasing. In other words, we have a negative first derivative, that means the original function is decreasing. So if the original function goes from increasing to decreasing, that means we would have a relative max. I think here it went from decreasing to increasing, right? And so we had a relative min. So we kind of just explained relative max. I'm just going to kind of skip that one. Again, relative max, again, on the left of the critical value, the original function is increasing. On the right of the critical value, the original function is decreasing, okay? And then we say that F has neither a relative max nor a relative min if F prime has the same side on either side of that critical value C, okay? So I know that's a mouthful. Like I said, I'm trying to get to an example. Let me see. First derivative test, right? So this is essentially what we're going to be doing. Say we have our C, which is our candidate for our critical value again. So relative min, if the original function is decreasing on the left and increasing on the right, then we have a relative minimum value. If the original function is increasing on the left and decreasing on the right, then we have a relative max. Okay. Notice here, on either side of our critical value, we have the same sign. So there's no max or min. Same thing here. No max or min. Right. So when we have our candidate for our critical value, if we have the same side on either side of that critical value, then there's no max or min. Finally. Okay. After 14 slides, we finally got to our example. Okay. So graph this function f given by this and find the relative extrema. Okay, so I think I'm just going to stick with the first derivative test. There are a lot of things that we can do to graph this, but I'm just going to focus on the first derivative test. So if we have our function, let's go ahead and find the first derivative, all right? Which, you know, we should be proficient at it by this point. So if we look at f prime, right, we'll go ahead and just take our derivative. We get what, 6x squared minus 6x minus 12, right? So the power comes down, subtract 1. So this is the derivative we have. So then if we want to find our critical value, the critical value is going to occur when the derivative is either 0 or it does not exist. So I think that, you know, the domain is all real, so it's always going to exist or whatever. But we can find out when this derivative is 0. So let's go ahead and set the derivative equal to 0 and solve. Matter of fact, I'm going to move this guy over here. I think that just makes a little bit more sense. So let's go ahead and set this guy to 0 and solve. So I'll put a 0 here. Now it looks like we can factor out a 6 from all of those terms. So if we factor out a 6, right, looks like we're left with what? X squared minus x minus 2. Can we factor that guy? Can we factor it like this? X and x. So now here, because my second sign is negative, that means my two signs need to be opposite. So one needs to be positive and one needs to be negative. Because my first sign is negative, that means what, my larger number is negative? We're looking for two numbers that multiply to give us -2 and add to give us -1. I think it's what, -2 and 1, right? So -2 times 1 is -2. -2 plus 1 is -1, okay? So then our candidates for our critical value, it looks like it's going to be what? -1 and 2. So what we're going to do, we're going to take a look at the number line, right? So say this is our positive x in this direction. We said what? X is -1 and +2. So here's our -1. Here's our +2, okay? So if we consider the first derivative, right? These are our zeros of our first derivative, right? So we got a 0 here and we got a 0 there. So these critical values, these candidates for the critical value breaks the number line up. Again, we got a 0 there and a 0 there. It breaks the number line up into 3 sections. You got this section A, right? You got this section A. You got this section B in between the -1 and 2. You got this section C, okay? Okay, so if we're going to do the first derivative test, I'm a little bit short on space. So we're going to start by picking some x value in section A, right? And plug it into the first derivative. So for instance, if we let x be -2, if we plug -2 into the first derivative, let's see. This guy is going to be negative. This guy is going to be negative. This is positive. So we have an even number of negatives. Ultimately, no matter what x value we choose there, we're going to get a positive result. We're going to get a positive result in our first derivative. So what that means is that our original function is increasing in that region A. Let's do that again for region B, right? So now we're going to choose an x value in region B. I'm a fan of choosing 0. Okay, we can choose 0. If we plug in 0, I just chose some x value between -1 and 2. 0 is usually easy to do. If we plug in 0 into the first derivative, this is gone, this is gone. We're only left with this 12. We get a negative result there. So the first derivative is negative between these guys. So that means that the original function is decreasing in region B. We got one more region, region C, right? Hopefully you're catching the drift now, right? We're going to choose something in region C, in other words, to the right of number 2, to plug into the first derivative. So something like 3. If we plug 3 into the first derivative, this guy is positive, this guy is positive, this guy is positive, right? So it's all positive, right? So that means the original function is increasing, right? Can you see the shape, right? So we're going from increasing to decreasing to increasing. So that means that the critical value, when x is -1, that's a relative max, right? This is a relative max, which means that when x is -1, that corresponding y value is larger than all the nearby y values. And then here, when x is 2, this is a relative minimum value, right? So that corresponding y value is going to be lower than all the nearby y values, right? So that's essentially the first derivative test. So we know that this graph goes from increasing to decreasing to increasing. We could also find, like, our intercepts. I'll just try to do a few additional problems. There's a lot of things that we can explore, but that's the meat and potatoes that we're looking for right there. Let me see. So I'll go ahead and find the intercepts. I'll just do this in another color. I'll do the intercepts. Sometimes they're easy, sometimes they're not. For instance, I like to start with the y intercept from the original. We'll do y intercept. So if we set x to 0, it looks like we get 0, 12. So it should cross the y-axis at 0, 12. Let's go ahead and see if we can easily find. If we can't easily find it, I'm not going to worry about it. We got to do some factoring. I think I'm going to not worry about it. Because I don't know that we can factor. I think I'm just going to use, at least my y intercept. I'm going to bypass. I'm just going to skip it for now. They're probably there, but I just don't feel like doing it. But I think all we really need is the max, the min. We can use the y intercept and maybe a few additional points. It would help if we had those intercepts. Let me see. But I don't think they're easy. Sometimes the x intercepts, let me think. We could use our calculator to just find those values or get an approximation. I'm going to do a rough sketch. Let me see. Factor there. I could factor out that, but that won't help us. We could approximate. Yeah, I mean, you could just use the calculator to find those extra steps. I'm going to leave that for you. For matter of fact, let me just go ahead and do it instead of trying to do it by hand. Nope. Right here. I'm gonna just use my calculator to find those. or just to get an approximation. Thank you. I don't have to go searching for that file. Okay, so my original, I have my 2x to the power of 3 minus 3x squared. Nope, it didn't hit the minus. Minus 12x plus 12, okay? I'm just gonna hit graph. I think this is a standard, so it's 10 in all directions. So we see we have a 0, like negative 2 point something, maybe like just shy of 1 and just about 2. We could do synthetic division. It looks like it's 2. Let me say 1, 2. I mean, about 3. Is 3 one of the zeros? We could do synthetic division. That's from college algebra. Let me just go to calculate. When x is 3? No. Okay, so it's not close. But again, we could use the calculator. Like if I go calculate 0 and then choose your bounds, you know. Because again, sometimes you can't factor it, and it's not like clean numbers. You know what I mean? And I think this is one of those cases. But I'm gonna hit enter. I just get an approximation. I'm just using my calculator, and then a guess. So -2. I'm just gonna use that as an approximation. So I'll just say approximately -2 point. I'll say 2818. 0. And then I think that was slightly less than 1. Calculate 0. And again, I'm just doing this just so we can use it. And we already have the image. Going to the right. I can get there. Okay, there it is. And then I guess that's good. Okay, so another 0. Again, these are all approximations. 9182. Okay. And then calculate 0. Here's the left bound. Here's the right bound. And I guess, okay, the last one is like 2.8636. Okay. And for those x-intercepts, I just use my calculator. Come on. Check attendance if it says Zoom user. I'm not gonna ignore. Okay, so again, I use my calculator to find those x-intercepts, but the y-intercept was pretty simple. We have our relative max, relative min, and then usually to kind of be complete, once we have, usually I do like x-intercepts and vertical isotopes. So just a few additional points between and beyond the x-intercepts, and then put it all together. So for instance, like when x is like -3, maybe when x is -1, and when x is 3, right? Find the corresponding y and then plot all those pieces together, right? I'll go ahead and do that. I'll do this in green. So again, we said when x is -3, we're going to find the corresponding y. When x is -1 and when x is 3, right? So again, what I did, I just chose some x values between and beyond those intercepts. Again, I use my calculator. I'm just going to go ahead and find the corresponding y. So that's going to be here. I guess I can calculate when x is -3. Corresponding y, okay, so that kind of goes off the chart, but that's okay. We'll just be aware of that. So when x is 2.2, that's fine. So you got a -33 there. When x is -1, we're at 19. And then when x is 3, it's probably going to go off the chart of 3. Okay. Okay. So then we just put all this together. We got our y-intercept, we got our x-intercepts. We have, we need to go ahead and identify our relative max and min. So when x is -1, right? Let's find that corresponding y. We probably didn't need the orange and the green. I just did that just to give us a better image. So when x is -1, the corresponding y is 19. And then when x is 2, the corresponding y look is -8. Okay. So we have our relative max, we have our relative min, we have our y-intercept. Again, we use the calculator to find the x-intercept, and then a few additional points between and beyond the x-intercepts and vertical asymptotes that we had. We're just going to put all this together. I think I need a copy of this so I can use it on another slide. So I'm just going to copy, and then I need a blank page. I mean, again, we've already seen the image, but I'm going to just show you how we put all this together. This is slide 14. Copy. Paste. Oh, and I got to go back and duplicate this again. Because I did the copy. Okay. Copy. Paste. And I'm just going to use this as a reference. Did I get everything I needed? I think so. I'll probably get rid of that once I'm done. Let me at least introduce some graph paper. And graphing can be a little bit tedious, so just do your best, do the best you can. Okay, our x values, like we go what, -3 to 3. The x values, like, they go from -3 to 3. We don't necessarily have to get that y value that goes all the way to 30, but like the maximum at 30 is probably good because our max goes up to 19. So I'll go on the y values, I'll go up and down to 30. Okay. All right. So then say, I guess the center's about here. The x value, we said, what, 3 and 3. So 1, 2, 3. I think that's enough. That's going to be enough. 1, 2, 3. Our positive x is in this direction. Okay. And then our y, we said 30. Let me see. If I went by 3s, that would be 10. If I went by 5, how many tick marks do I want? Let me see. 1, 2, 3, 4, 5. So 6s. That's fine. 1, 2, 3, 4, 5. So each tick mark is going to be 6. Our positive y is in this direction. Okay, positive x is there. Again, this is like this is the origin. This is 1, 2, 3. These are negative. These, I think, went by 6s. Let me see, 6, 12, 18, 24, 30. 6, 12, 18, 24, and 30. These are negative. Okay. So then we're just going to, all the information that we found before, we're just going to put it all here. Okay. I guess I can match the colors. I think that'll be okay. So we can do the y-intercept, for instance. The y-intercept was 12. Okay. We had a relative max, -119. So 19 is right about here. And I guess we can label it -1, 19. This was 0, 12. Okay. It looks like 2, -8. So 2, -8. Is that halfway? 9. Okay, so -8 is about here. Okay. So we got our max, our min, these intercepts. Let me see. -2 point something, 2.2. So that's about here. This is -2.2818, 0. Okay. We had what, 0.91, which is about here. 0.9182, 0. And then my space is a little bit off. I'm going to shrink this down. Almost. Nope. Okay. And then this last one, 2 point something, 2.86. So about here, 2.8636, 0. Okay. So then from there, we know we have a max, min, we have those intercepts, and then we just connect it with the smooth curve. Oh, and these a few additional points. So -3, -33. So that's going to be a little bit off the chart. It's about like somewhere down here. -3, -33. -119 is about here. Wait a minute. Oh, that was our max. Okay, that's fine. We already captured that one. We probably should choose some point other than -1, but we'll go with it. It's okay. And then 3.3. So 3.3 is about here. Okay. So then we just connect those with the smooth curve. Again, we already know what the image looks like. I'll choose this color. So it starts. Passes through this point, passes through that point, through our max, through the y-intercept, x-intercept, and I think we already have a digital version of that. I think I'm gonna leave my notes there, and I'll include a screenshot of this. Let me match the window. So minimum, we can go like negative. Let's go -4 up to 4 in steps of 1. Let's go negative. Let's go -40 actually, up to 40. And each take mark is 6. Okay. So I'll include that in the notes. So again, you know, it could be a little bit extra. You know, we're gonna be working in my math lab. The main takeaway is just being able to use the first derivative test. Let's try to get another one in. I see the time. What's going on? Where'd it go? Okay, it's on the previous slide. Cut, paste. Okay. Let's shrink you down. Let's get rid of these lines right here. Okay. Get rid of this. I'll leave that for a reference. So this is us doing it by hand. You saw where, again, we use the calculator for the intercepts, and we have a digital, and we have our little reference there, okay? So, and let's kind of recap. Let's see what the textbook did. I see it's really time to go into the next section, but I kind of want to do another one. Okay. So what the book did, they just chose several values of x, found the corresponding y, and they made sure to include the relative max and min, right? So where we found the intercepts, we didn't need to go into those details. I just did that because that's what I wanted. But notice they didn't even exclusively find the intercepts here. I think they found the y-intercept because that one was simple. But again, they just chose their x values, found the corresponding y, plotted. They essentially just plotted points, right? And highlighting the relative max and the relative min. That's fine. Okay, I think, yeah. Right. And then they just recap in the first derivative test. Okay, I kind of want to try at least one more. Find the relative extrema for this function given by this, and then sketch the graph. Okay, so maybe we'll try the technique that they did. So let's do one more for the relative extrema. Again, we're doing, so relative extrema means find the max value and the minimum value. So first thing we want to do is find the first derivative. So then f prime of x. The 2/3 comes down. I'm gonna have this x minus 2 to the power of a negative 1/3. That's it, right? Hey Google, change the light color to soft white. So, hey Google, change the light brightness to 100%. Okay, that's fine. Oh, hey Google, stop the alarm. So then the relative. Hey Google, stop. Okay, I think she heard me. Hey Google, stop. Thank you. Okay. Okay, so again, the relative extrema are going to occur when the first derivative is either 0 or undefined. Let me rewrite this guy. This we got this cube root x minus 2. You got a 3 here and a 2 here, right? So now, because we had that negative exponent, it's essentially a rational function, where the radical is in the denominator. So something like this, it won't ever be 0 because in order for a fraction to be 0, the numerator would have to be 0. But I think we could find an x value where this guy is undefined. In other words, it'll produce a 0 in the denominator, right? So it looks like when x is 2, right? When x is 2, it produces a 0 in the denominator, so that'll be our critical value. Okay? I'll highlight it. So our critical value is going to be what? When x is equal to 2, because it creates a 0 in the denominator. So then when we go to do the first derivative test, we're going to plot this critical value on a number line. Again, this is our positive x. When x is 2, right, our first derivative is what? 0. Nope, it's undefined for that value, right? Okay, so then what we want to do, we want to see how does the original graph behave on either side of this candidate for a critical value. So a number to the left, that might be simple to test, was like when x is 0. Let me see. The cube root of a negative is negative. It looks like we're going to ultimately get a negative there. All right. So here, no matter what x you choose, we should get a negative result over here, which means the original function should be decreasing. A number on the right to test would be a number like 3. If we plug a 3 into the first derivative, it looks like we get a positive result. 3 minus 2 is a 1. Cube root of 1 is 1. We get a positive answer. So what that means is no matter what x we choose over here, we're going to get a positive result in our first derivative. So that means the original function should be increasing. So it looks like the original graph goes from decreasing to increasing. So this should be our relative minimum value. When x is 2, we plug it into the original to find the corresponding y. So we could make a table of values like the previous example did, where we're going to focus on x equals 2, just find the corresponding y's, plot the points. All right, we can do that. And I feel like that's a lot more simple than. Now, the y-intercept here, when x is 0, it gets a little. I think the simple thing is just, just choose the simple values of x and plot those points. I think that's a simple thing here. This is slide 23. I just want a blank page. I guess I can take this one. Copy. Paste.
Professor, can I ask you a question?
Yes. No.
My phone is about to die, but I'm gonna join right back in like 5 minutes on my laptop. Is that gonna like mess with the attendance? Or
no?
Oh, okay.
Make it.
Right. Appreciate it.
Okay, so yeah, we're just gonna plot points like they did in the previous, right? Just make it simple, right? I know a lot of this stuff seems complex, but complex is really what we consider to be complex is really just a long string of simple ideas. All right. So the name of the game is to try to keep it as simple as possible. All right. So if we can get the job done, we found okay, it's not gonna work because I gotta do this. Okay. We found our extrema, right? So we know that when x is 2, we get a relative min. So I'm just going to make a table of values and highlight the relative min and call it a day. Right? Our x versus our f of x. We can do a vertical, that's fine. Okay. So we said, well, when x was 2, let me see. 1, 0, we'll go 3 on either side. So we'll go like -1, 0, 1, 2, and then 3, 4, 5, right? And we just find the corresponding y, plot the points. So then for that, I'm going to use my trusty dusty rusty. So that was a lot more smooth than the first one. Parentheses x minus 2 to the power of 2/3. Okay, plus 1. Okay. And I want to invite, I guess I could just look at the table. We started at -1. Okay, that's fine. We'll work with it. 0801. These are all approximations. 3.0801. 2.5874. Okay. Then when x is 1, we get 2, 2, 1. Notice that our minimum value is the lowest y value for all the nearby y's. 3, 2. 5874. And then 3.0801. Okay. So symmetric. Okay, that's fine. I'll just do a rough sketch. I think there's a horizontal asymptote. It looks like there's a limiting, but let's see. Here's our positive x. I'm just going to do a rough sketch because I'm trying to get to the next section. Here's our positive y. Horizontal. I'm not going to go that far, but we can at least plot these points. Let me see. 1, 2, 3, 4, 5. Kind of need to go a little bit like this. Let's see. 1, 2, 1, 2, 3, 4, 5, 6, 7. That's a little bit extra. Let me read it. Let's see. 1, 2, 3, 4, 5. That's decent. 1, 2. Our y values pretty much the top part. So like 1, 2, 3, 4. Here's the origin. 1, 2, 3, 4, 5. 1, 2. This is a rough sketch. I'm not doing this one to scale like I did the last one. This is a positive y. These guys are negative. Okay. So -1, 3.08. So that's about here. 0, 2.58. 0, 2.58 is about here. 1, 2 is here. And then over 2 up 1. This is the relative minimum. We can highlight it. We can say relative minimum. Okay. And actually, like that, that's fine. Okay. And then, so next was 2. Then we had 3, 2 was here. And then 4, right, it's all symmetric. So that's about here. And then here, right? So we get an image, something that's behaving. So we're passing through there, our relative min. So again, we just plotted points. We identified our relative min. Yeah, right. So this was us doing it by hand. Let's see what the textbook does. They found the first derivative. So again, the critical values occur when the first derivative is either 0 or undefined. There's no value of x that's going to make that 0, but we could find a value of x that made it undefined, namely when x was 2. That was our critical value, so we did a test on either side. We got that the original function, we got a negative first derivative on the left, positive first derivative on the right. So that means the original function went from decreasing to increasing, which means we had a relative minimum value. So that 2, 1 was our relative minimum. Oh, okay. So it's a point. We got close. We definitely messed it up. Okay. At least I didn't do the asymptote. I'm gonna just edit that. But that's not too bad. And if we took more points or more values, we got a better image. But that's still fine. I mean, that's still pretty close. So something like that, and then like that. That's fine. Okay, not too bad. And see, they did the same thing. They chose the x, plotted the corresponding y. Now they say they did more points, right? We just did the 1, 0, the integrals, the integers. but they did the half integers or like the halfway points between all those as well. Okay. All right, so we kind of do need to go into the next section. I just want to do a scan here. So these are a lot of quick checks, so I usually leave those as exercises. So relative extrema, again, first derivative, find where the first derivative is either 0 or undefined. Once you have your extrema, just choose several values of x, find the corresponding y. They just pretty much just plotting points. That's kind of what they've been doing. So you can see it here. So once they found the extrema, you plot the points, all right? Okay, so that wasn't too bad. There was only one example we didn't do there. Okay, so I'll make a copy of this available momentarily, like once we're done with class. Let's go ahead and hop into the next section, and the final section for today. It's losing her mind over there. View settings, single page. Okay. All right. Okay, give me just a moment. I'll be right back. All right. Who won? Did you win? She's like chasing her tail. Okay, so again, with the previous section, we were looking at the application of the first derivative. And basically, the first derivative was telling us whether the original function was increasing or decreasing over an interval, right? And we also identified critical values. The critical values occur where the first derivative was either 0 or where it was undefined. So the first derivative test identifies the relative max, min, where the original function is increasing and decreasing. We put all that together to get our images. Okay. So then here, so again, 3.1, we were using the first derivative. So now here in section 3.2, we're going to explore some applications of the second derivative, right? So first derivative tells us increasing, decreasing, max, and min. Now we want to see, well, what does the second derivative tell us about the original function, original graph? So section 3.2, using second derivatives to find max and min values and sketch graphs. Okay. So a few objectives. One, classify the relative extrema of a function using the second derivative test. And then two, graph a continuous function in a manner that shows concavity, right? So I'll just go ahead and give a summary on what the second derivative tells us. The first derivative tells us increasing, decreasing, constant, things of that nature. Second derivative tells us if the original function is concave up or concave down, right? So concave up is like if you have a cup, the cup opens upward, right? That's going to occur when the second derivative is positive, all right? Concave down means the original function, the cup opens down. So the second derivative tells us which way is it concave up or is it concave down, okay? So suppose that a function f, whose derivative f prime exists at every point on the open interval I, then we say that f is concave up on the interval I if f prime is increasing over I. In other words, if the derivative of the derivative is positive, then we say that the original function is concave up. In other words, if the second derivative is positive, the original function is concave up. See how it's kind of like a cup? The cup opens upward, like you can pour water into it or something. And then we say that f is concave down on the interval I if f prime is decreasing over the interval I. So the first derivative, the derivative of the first derivative is negative for all values in there. In other words, if the second derivative is negative over the interval, the original function is concave down. So the cup opens downward. It's like you're pouring your cup out. All right. If our cups are already filled, then we can't learn anything. So sometimes we need to pour our cups out so that we can learn something new. All right. Anyway. Okay, so a test for concavity. So this is like the second derivative test. If the second derivative is positive on some interval, then the graph of f is concave up. In other words, f prime is increasing, so f is turning upward on the interval. If the second derivative is negative on the interval, then the graph is concave down, right? So again, second derivative positive is concave up, the cup opens upward. If the second derivative is negative over an interval, the original function is concave down. In other words, the cup opens downward. Right. So First derivative tells us increasing or decreasing. Second derivative tells us if it's concave up or concave down. Okay, so the second derivative test for relative extremis. So suppose that f is differentiable for every x in the open interval from a to b, and there's a critical value c in the open interval from a to b, such that f prime of c is 0. Right. So the first derivative is 0. That means that we're either working with either a relative max or a relative min. Right. So say that critical value f of c is a relative minimum value. That means it's the bottom of the valley, which means the original function should be concave up, which means the second derivative should be positive. All right. So again, we have a relative minimum. The second derivative should be positive. So we have an interval, one critical value. That critical value is a relative min, so the original function should be concave up. F of c is a relative max if the second derivative is negative, right? So if you're at the top of a mountain, it should be concave down. The cup opens downward. We have a relative max. Okay. Whenever the second derivative is 0, then we have the first derivative test can be used to determine whether f of c is a relative extrema. So if the second derivative is 0 and we're still trying to find a local max or min, then we default back to the first derivative test to determine if it's a max or min. Okay. So the second derivative test, you have an interval, you have a critical value. If the second derivative is positive, cup opens up, that means you have a minimum. If the second derivative is negative, concave down, that means you have a max. If you get 0, then you got to use the first derivative test to determine if you have a max or min, to determine if you have an extreme. Okay, kind of a mouthful. Let's see it in action. Graph this function and find the extreme. Okay, so with this, we'll probably use we'll go ahead and find the first derivative, the second derivative. We'll try to use the second derivative to test to see if our critical values work. If it doesn't, then we have to use the first derivative, okay? All right, let's see. Let's go ahead and find our derivatives. So our f prime is going to be 3x squared plus 6x minus 9. And then the second derivative, 6x plus 6, okay? So our critical values are going to occur when what? The first derivative is 0, okay? Looks like we can factor out a 3 from all of those terms. So I'll just draw an arrow so you know that that's what we're working with. I'm going to factor out my 3. I have my x squared plus 2x minus 3 equals 0, okay? Can we factor this guy? The second sign is negative, so our sign should be opposite. The larger should be positive. It looks like it's a 3 and a 1. These multiply to give us -3, and they add to give us a +2, so this looks good. So our candidates for critical values looks like it's what? X equals -3 and +1. Okay, so then we can use the second derivative test to see if those are any extrema. I'm going to work up here. Okay. Again, this is our positive x in this direction. We want to explore when x is -3 and when x is 1. And we're going to actually start with the second derivative. Okay. So if we plug -3 into the second derivative, what is that? A -18 plus 6. Ultimately, that result is negative. Right? Let's what color? Okay. So we got that -3 was negative in the second derivative. That means the original function is concave down. Okay. If we plug 1 into the second derivative, we get a positive result. Original function is concave up. Okay. So the negative, when x was -3, we're saying the original function is concave down. So that implies that that should be a relative what? Max. That's going to be a relative max. And this is going to be a relative minimum. That's using the second derivative. Okay. We can find out. So, and we're just going to make a table of values and plot the points. That seems to be the simple thing here for these examples. So our table, I'll do it in green, I guess. We're going to go x versus f of x. So the main ones we need are when x is -3 and 1. So we'll go like, let's go -4, -3, -2, -1, 0, 1, 2. And let's go ahead and do 3 as well. And find the corresponding y's for those guys. So I'll use this guy. Okay, so what we got x to the power of 3 plus 3x squared. Nope. Y equals 3x squared minus 9x minus 13. Okay. And I'm just going to go to the table since I know everything will be there. Okay, we started at what, -4? I low-key want to include -5. Are we missing a 0? Wait a minute. We're missing a critical value? Oh, our x-intercepts. So that's one y. Okay, I am going to include -5 since we get a sign change there. Yeah. I'm going to include -5. So that is good. Okay. Okay. So then we get a -18, 7, 14, 9, -2, -13, -18. Need 2 and 3. -11 and 14. Got lucky with those zeros. At most, what, 3 zeros? 1, 2, 3 sign changes. Okay, so I think we're okay. I think we've at least captured them. And then we just put it all together. So our x's went from like -5 to 3. The y, the lowest value, looks like it's what? Is it -18? So maybe 20 on the y-axis. I think I'm just going to do a rough sketch. So my positive x is in this direction. We'll do a positive y in this direction. Okay. Our x values, we need to get like at least 5 or so. Let's see. 1, 2, 3, 4, 5, 6, a little bit extra. 1, 2, 3, 4, 5. Okay. Y's, we're trying to get to 20. So I'll probably go by 5s. Let me see. 5, 10, 15, 20. 5, 10, 15, 20. Our origin, kind of out of space. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 5, 10, 15, 20. 5, 10, 15, 20. These are negative, negative. A little bit jammed. Obviously, I should probably give myself more space, but we're going to go with it. We got our relative max, our relative min. I might highlight those in purple. Matter of fact, when x is -3, so this was our, this is one of them, and when x is 1. Okay, style. We'll do that in purple. We'll put this back. Okay, just to make them pop. -3 is there. Min is here. Okay. All right. I think I'm gonna do those first. -3, 14. It's like here. And then 1, -18 is like here. A few additional points. -4, 7. It's about here. -5, -18. Like here. Yeah. So relative min means like the nearby. Even though we could find x values that go lower, but it goes down to negative infinity up to positive infinity. But relative max and min just means like in the local area. So it's like the peak of a mountain, bottom of a valley. These are this not to be confused with absolute max and min, which is coming up. Absolute max and min is a little bit extra condition that we need to find absolute max and min. Okay. 3, 4. When x is -2, we're at 9. -1, -2. We're totally out of space. It's about there. 0, -13. 1, 2, -11. It's about here. 3, 14. And then if we put all this together, do a different color. So basically, it passes through. There's our max. I'm gonna highlight real quick. This is a relative max. This is our relative min. Okay. And that's so I kind of like what the way that the book is doing. Again, we're just exploring first derivative, second derivative, and what it tells us about the original graph. Then they're just plotting points at that point. They're not even really focused on like the intercepts. There are a lot of other concepts that we could talk about, but just to kind of simplify things for this discussion, identifying the max and the min, and then plotting points. Okay. And again, we just chose the x values, found the corresponding y's, put it together. Okay, I want to kind of start with the image. And I think we got the same thing. Man, I feel sick like all of a sudden. But it's the temperature, like it just keeps changing so much. Anywho, so notice they plotted their max and their min, then using the table of values, they plotted everything else. And they essentially did the same thing we did. So. Oh man, we got like 10 minutes. Okay. Find the extreme. I'm gonna put a pin in this. I'm gonna have to come back to this one. I just want to kind of see. I want to do a quick scan. Points of inflection. We need to talk about this. So the point of inflection. So the first derivative, when the first derivative is either 0 or undefined, that tells us like does a critical value are candidates for either a relative max or relative min. For our critical values for the second derivative, those occur again when either the second derivative is either 0 or undefined. And our critical values for the second derivative, these are going to be what's called our points of inflection. So the point of inflection is where the original graph goes from either concave up to concave down, or vice versa. It goes from concave down to concave up. All right. So second derivative critical values identify our points of inflection. It's similar to the first derivative test. It's just in terms of the second derivative. That's the synopsis there. So with the second derivative is either 0 or does not exist. Okay. Quick check. Quick checks I usually leave for you. I'm gonna go through this in just a moment. Find the relative extrema. Okay, I think I'm gonna take some time to find this extrema here. Let me I want to kind of like peruse through this strategy for sketching graphs. Let's see what it says. So if we're trying to sketch a graph and we want to be detailed, derivatives and domain, find f prime and f double prime, and know the domain of the original function. Find the critical values of f by solving f prime as 0 equal to 0 or where it does not exist. Then you can find it. So the first derivative tells us whether the original function is increasing or decreasing. You can use the second derivative to determine if it's a max or min. And then you can also use the second derivative to find your points of inflection. And then you can identify whether the original function is concave up or concave down, and then put all that together, right? So again, just exploring the first derivative and second derivative. First derivative tells us our max and our min. Second derivative tells us our point of inflection. And then, once you have those critical values, identify what they are, a few additional points, and put them together, okay? Kind of a speed run because we're kind of out of time. We got like a few minutes. We really have like 7 full minutes. So I'm gonna do the best I can. Find the extreme of the function and then sketch the graph. So in other words, we're gonna explore the first derivative and the information that we get from there, second derivative, information that we get from there, and then a few additional points and put it all together. Okay. So let's go ahead and find our first derivative. Clean it up just a bit. First derivative is what? 3x squared minus 3. Remember when we first introduced this and we had the whole, something like this would have taken up the whole page with the limit as h tends to 0 of the difference quotient. Now we just look at it, and that's what I was trying to encourage you. I was like, don't be intimidated by this difference quotient. We have techniques you can look at it and just get the answer. So that's what we just did here. Let's go ahead and take a look at the second derivative. That's going to be 6x. I think that's it, right? 6x. Okay. So critical values from the first derivative, we can factor out that 3. We're going to have what? X squared minus 1 equals 0. So I think this factors into x minus 1 times x plus 1. So then we get x equals plus or minus 1. Those are critical values from the first derivative. Let's go ahead and find our critical values from the second derivative as well. So our critical value from the second derivative is x equals what? 0. Okay. So that's our candidate for it. So our numbers we're going to explore are -1, 0, and 1. Okay. So we have our come on, positive x in this direction. Here's our 0. Here's when x is -1. X is 1. We want to see how this behaves. We can consider the original function. We can consider the first derivative and the second derivative. Okay. So now the plus or minus 1, those are zeros in the second derivative, right? The first derivative. So this is our 0 in the first derivative, our 0 here, right? So then a number to test on the left is like when, actually, let's plug -1 into the second derivative. Right there. So if we plug -1 into the second derivative, we get a negative result, right? So this guy is negative here. Let's do this in green. Which means the original function is concave down. If we plug 1 into the second derivative, we get a positive result. So this guy is concave up. If this is concave down, that means that this is what? A relative max. So I'm going to say that this is a relative maximum value here. The corresponding y from the original looks like a 0. Okay. If this is concave up in the second derivative, that means we should have a relative minimum value. It's going to be a relative minimum value. Right. So the corresponding y there is also 0. Okay. I think that this is 0. When x is 0, this is 0 in our second derivative. So that's our candidate for our point of inflection. Okay, on the left of 0 is concave down. On the right is concave up. So this is our point of inflection. So this is indeed, that's how we verify that this is our point of inflection. Okay. And the corresponding y there from the original is 2. So we have our point of inflection, we have a relative max, relative min, and we'll make a table of values. So we'll probably go from like -2 to 2, and probably in the half tick marks as well. Yeah, we just need our table of values at this point. I'll go ahead and do my table here. Okay, so we're gonna do what, x versus f of x. I see the time. Let's go -2, -1.5, -1, -0.5. I'm out of space. 0, 0.5, 1, and then 1.5. I'm gonna try to squeeze 2 in there. Okay. Then I'll use my calculator. Nope, not that. Here, we got this x to the power of 3 minus 3x plus 2. I go to my window. Table set. I want the table to start at -2, and I wanted to change by 0.5. I'm gonna hop over to the table. Okay. We probably should have did -3 just to get that sign change. But we're kind of out of time and space. So, okay. So the corresponding y's. Let me see. So we get a 0 here, 3.125, 4, 3.375, 2. Okay, let's keep going. 0.625, 0. Get up to 2, 0.875, and 4. Point of inflection, relative max. Okay, what I'm gonna do, I'm trying to get you out of here. I see the time. I'm gonna do my max in purple. I'm gonna do this in purple. I'll do the point of inflection. I'll do it in orange. Okay. So this guy, -1 and 1. So that one, those need to be in purple so we can see it. 0 is our point of inflection. Trying to get you out of here. I see the time. And this needs to be black style. Okay, I think I'm gonna use my prepared notes just for the sake of time. Trying to get you guys out of here. Oh, come on. Okay, black. Okay, so I'm just gonna have to trust that this is good. We got a relative max, -1, 4, relative min, 1, 0. Yeah. And then the point of inflection was 0, 2. And I'm just going to jump to the image for my prepared notes. If I can. Here it is. -1, 4, 1, 0, 0, 2. And they have a similar graph. We did the halves, they did the integers. We're good to go. Let me just do a quick scan to see if there's anything else that's pertinent. Quick check is an exercise. So more of exploring the first derivative and second derivative. It's a little bit involved, so just, give it a go. Give it a try. Okay, so it was really only one example that we didn't explore. Any burning questions before we go our separate ways? I'm gonna have to nurse myself back to health. I don't know. I just got nauseous all of a sudden. So again, is there a question? Go ahead.
Yeah, I just wanted to know, I'll join like 3-4 minutes late. Would my attendance still be counted?
Yeah, it's fine.
Okay.
Yeah, so today we explored the first derivative and the second derivative. The main takeaway from today, the first derivative tells us whether the original function is increasing or decreasing. We can use it to find the local max and the local min. The second derivative tells us whether the original function is concave up or concave down. We can use it to verify that a critical value is either relative max or min, and we can use the second derivative to find the point of inflection. So first derivative test, second derivative test. So that's what we kind of did today, okay? Okay, so aside from that, if there aren't any other burning questions, we're going to go ahead and end the session here. Now, from one beautiful mind to another, we're going to go ahead and end the session here. We'll meet back on Wednesday to go through the next two sections. So sections 3.3 and 3.4. The recommendation, go ahead and watch the recording associated to those so that when we're live, it can be a review. All right, guys, take care and see you on Wednesday.
Have a good one, Professor.
Yeah, have a good one.
Uh-huh. All right, so I'll update attendance and everything a little bit later. I got another class in like a few minutes.